Here are a few problems solving for the moments of inertia. What's useful about these problems is that the configuration is the same in both cases. We have four masses arranged in a square pattern with a length L in between each of the masses. But what's different in these two problems is the axis of rotation, which is the important part for calculating the moment of inertia, because we know that the moment of inertia is the sum over these I masses for each mass times its radius, its distance from the axis of rotation. In this problem, the axis of rotation is here, so the distance r is the hypotenuse of this triangle with L over 2 by L over 2 length. So if we write r equals the square root of L over 2 squared plus L over 2 squared, that's L squared over 4. There are two of them, so that equals the square root of L squared over 2, which is equal to L over the square root of 2. Now he writes it a little bit differently in the slides as square root of 2 over 2. The way to get that is if you multiply top and bottom by square root of 2, you get square root of 2 over square root of 2 times the square root of 2, which is this. And this is actually a useful relationship to remember. L over the square root of 2 is the same as square root of 2 over 2 times L. So anyway, we plug that in. If we sum over all four masses, since the masses are identical, we get 4 times each mass times its radius squared, which is 4m times square root of 2 over 2l squared, and that comes out to be 2ml squared. In this problem, where the axis of rotation is this way, the radial distance of each of the masses is L over 2, L over 2, L over 2, and L over 2. So again, we sum over mr squared. Again, they're identical, so we can put this factor of 4 times m times L over 2 squared, which is 4m times L squared over 4, which just equals ml squared, and that is the solution for the problem.